Ladies and gentlemen, welcome to show number 211 of the ARC Junkies Podcast. Today, I'm talking about the various types of weld discontinuities and defects, what causes them, and how to eliminate them. Regardless of how long you've been welding, you've no doubt made a welding discontinuity or a defect. It happens to the best of us. But knowing what causes them and how to eliminate them is going to make you a much better welder in the end. We'll get right into it after a quick word from the supporters of the show. Today's episode of the ARC Junkies Podcast is brought to you by Rockmount Research and Alloys. I get questions all the time about what's the best welding rod for cast iron and cast steel. And you know what? Rockmount makes the best cast iron rod to get the job done right the first time, every time. Check out their Jupiter AAA. This electrode is suitable for all ductile, malleable, gray cast irons, and steel to cast iron applications. The Jupiter AAA has the tensile strength of up to 70,000 pounds per square inch without overheating the electrode. It features a smooth, ductile deposition on steel to cast iron applications. You'll get efficient deposits on all weldable grades of cast irons. The Jupiter AAA provides machinable deposits and eliminates porosity. The Jupiter AAA is engineered to give the user high-strength ductile welds without overheating the electrodes, thus producing a more effective deposit that's machinable. Its welds are much smoother and usually free of porosity and has a smooth, flat appearance. The Jupiter AAA makes it easier and more cost-effective to do large cast iron repairs. It can be used on dirty, oil-impregnated heavy pieces. It's the superior choice for joining cast iron to steel. You can find out more on the Jupiter AAA and all the other great rods and wires Rockmount provides by going over to their website, rockmountwelding.com. And don't forget, you can get Rockmount rods and wires at MSC Direct and get free shipping right to your door. We're also brought to you by Everlast Welders. Everlast has a machine for every budget and every skill level. They currently carry everything from stick, MIG, and TIG welders to multi-process machines and plasma cutters. They even offer financing for small businesses with no obligation and instant credit decisions. In addition, Everlast is always offering excellent deals and sales on many of their machines. You can check out their website today to see which machine is right for you. Most of their machines are single-phase and can operate on 110 or 220, making them perfect for your at-home garage or small shop. Everlast is a great option for the small business owner to get you up and running in a flash. Regardless of the material you need to weld on or the process you need to run, Everlast has what you need, and they offer a 5-year warranty on all their IGBT inverters. Head on over to everlastwelders.com to get your machine today. And don't forget, if you pick up any machine that comes with a stock foot pedal, you can use ARC Junkies in the comment section to check out and get that free Nova foot pedal and TIG torch upgrade absolutely free. Everlast Welders. Weld mean, weld green. We're also brought to you by ISOTUNES, makers of Bluetooth hearing protection that are OSHA and NIOSH compliant to be used as hearing protection in the shop or the job site. They make hearing protection for outdoor shooting and motorsports as well. You can get $10 off your first pair by going to isotunes.com and using ARC Junkies 10 in the discount box at checkout. Now you can protect your hearing and listen to your favorite podcast or playlist. That's isotunes.com. We're also brought to you by Lincoln Electric, the welding experts. Lincoln recently released some really cool machines for field use. The all-new Ranger 330 MPX is built for all seasons. The advanced electronic fuel injection engine drive delivers quick starts, improved fuel efficiency, and optimal performance in high-altitude applications and extreme temperatures. In addition to the engine, the modern design and advanced features allow this machine to streamline welding operations and improve efficiency on the job site. The Ranger 330 MPX has up to a 20% smaller footprint and is 25% lighter than other machines in its class. It transports to the field with less bulk and less effort, leaving you more room for other tools and accessories you're going to need on the job site. It's smarter. The Ranger 330 MPX has a digital user face that offers a suite of advanced technologies that improve weld performance and productivity. Some of the performance-boosting technology is quick setup with ready, set, weld. Arc Effects technology where you can actually see what the volts, wire feed speed, and amps actually does to your puddle in your weld. It's capable with crosslink technology and chopper technology. And it has high-quality operations such as clean AC generator with up to 10 kilowatts of continuous power. Plenty of power at 330 amps and 28 volts for 100% duty cycle to weld quarter-inch 7018 electrodes. The Magnum Pro 250 LX GT Direct Connect spool gun, and arc gouging capabilities up to 3/16 carbon electrode. The new Ranger 330 MPX is also up to 60% quieter than other machines in its class to enhance safety and comfort in the workplace. You can get your 330 MPX today, along with a 10% discount, by going to store.lincolnelectric.com and using ARC Junkies 10 in the discount box at checkout. You can save 10% on all welding machines and fume extractors. In addition to that, you can save 20% off all your gear and consumables by using ARC Junkies 20 in the discount box. That's store.lincolnelectric.com. Lincoln Electric, the welding experts. All right, you know what time it is. Fire up your machine, drop your hood, and turn me up 5.
This is David Malero, and you're listening to the ARC Junkies Podcast.
You're listening to the ARC Junkies Podcast, helping you make every weld better than your last with each episode. And now your host, Jason Becker.
All right, ladies and gentlemen, today we're going to be talking about a couple things. I want to discuss weld discontinuities, weld defects, non-destructive examination, and destructive examination. So what is a weld discontinuity? A weld discontinuity is something we've probably all made in the past, whether it's lack of experience, lack of knowledge, or, sometimes things just happen, right? So in order to eliminate weld discontinuities, we have to know what they are and how to avoid them. What causes certain weld discontinuity. So that's what I wanted to talk to you all about today. So a weld discontinuity, the very definition, is an interruption of the typical structure of the material, such as lack of homogeneity in its mechanical, metallurgical, or physical characteristics. And a discontinuity could be the result of a defect, but it's not necessarily a defect. So, which leads us into our next topic, what is a weld defect? And a weld defect is a discontinuity that by nature or accumulated effect, for example, total porosity in a length, renders a part or product unable to meet minimum applicable acceptance standards or specifications. A defect results in rejection of the part or product. So we have to understand that not all discontinuities are defects, so we can't automatically reject them for having a discontinuity, whether that's undercut, porosity, anything like that. However, when they're accumulated, when we start adding that up, what's the size of the porosity, the percentage of porosity for the given length that we have, or how much undercut can we have. Those are considered defects, and that's what can cause a part to be rejected. So in certain codes, you're allowed to have a certain amount of porosity. You can have a certain amount of undercut. So those are discontinuities, but we can't reject them because of that, right? So, but if we add them up and it becomes a defect, that's when the weld is rejectable, and we're going to have to cut it out or redo it or repair that weld in some form or fashion. Some of the welding discontinuities that I want to talk to you all about today are porosity, which I'm sure we're all familiar with. We've seen that, undercut. We're all familiar with that one because anytime we post a picture on Instagram or Facebook, that's the first one-line comment that comes out of somebody's mouth, right? Every weld's got undercut. If you put a picture of a weld on social media, it's got undercut automatically. But I mean, that's not actually the case. We're also going to be talking about incomplete fusion, incomplete joint penetration, excessive reinforcement, which applies to groove welds only, underfill, that's also going to apply to groove welds only, a concave roof surface, also known as suckback, it's a non-standard term as suckback, and then overlap, arc strikes, and slag inclusions. First up, let's go ahead and talk about porosity. What is porosity? Porosity is a cavity-type discontinuity formed by gas entrapment during solidification. These trap gases in the molten metal may form bubbles or pockets as the weld solidifies. So we've all seen that. You got the tiny little pinholes in there, or it could be a little bit bigger. It's like the little pores on the weld surface. So what causes porosity? Well, the first thing is dirty base metal that's been contaminated with hydrocarbons such as oils, grease, or paint. So anytime we prep a joint for welding, right, we're trying to set ourselves up for success. So we want to take off mill scale, we want to take off any oils from the factory, any grease, especially if this part's been in service for a while, or any paint. We want to get rid of that stuff and take everything down to bare base metal. That's going to help us relieve or alleviate porosity. Now, in addition to that, moisture on the joint surface. So if we have water or anything else on there, you might want to get rid of that. You can do that by, heating up the base metal, not like a preheat or anything, just kind of like heating it up to dissipate any moisture that's on there. Also, you want to make sure that you don't have any moisture in your electrodes. And I talked about that, when I talked about what the F number, Just the Tip Tuesday episode, what the F number. We want to make sure that we're using low hydrogen electrodes. So we want to make sure that we don't have any moisture in our rods. Now, if you're using like a 6010 or something like that, it doesn't require you to put it in a rod oven, but you still want to make sure that all of your rods, wires, electrodes, they don't have any moisture on them whatsoever. So if they have water on them, get rid of them, use something else. In addition, insufficient or improper shielding gas caused by an inadequate shielding gas flow rate, gas that's contaminated from its source of delivery, or wind or a draft that prevents the gas from adequately protecting the molten weld metal. In addition to that, if our cubic feet per hour, our gas flow, because I know folks across the pond, they use liters per minute. If our gas flow is too high, that can also cause porosity because that creates something called the Venturi effect, where the force of that gas coming out of our nozzle is actually creating a vacuum as it's coming out. It's coming out so fast, it creates a vacuum. Very similar to, think of like a sandblaster. You've got that tube hooked up to the bottom of the hose or the bottom of the gun, and when you step on the foot pedal, it blows air across that, creating a vacuum. This can do the same thing with shielding gas, and it pulls contaminants from the outside. It pulls outside atmosphere into our weld pool. That's something we want to avoid. So making sure we have proper shielding gas and proper gas flow is going to help eliminate porosity. Addition to that, incorrect welding conditions or techniques, such as arc length. Arc length is such a huge factor in pretty much all of the weld discontinuities we're going to talk about. So if my arc length is too far back, that means I'm not getting adequate gas shielding. For like flux core gas shielded or gas metal arc welding, but also with stick welding, because as we're melting an electrode, that's going to create CO2. That's where our shielding gas is coming from. And we want to make sure that we maintain a proper arc length, so as that flux burns off and creates that CO2, it's within our weld pool area. So we want to make sure we maintain a correct arc length. So that's one thing we can do to eliminate porosity. There's actually 4 major types of porosity. Okay, so you look at something, you say, it's porosity. Yeah, but there's actually 4 different types of porosity, and that's uniformly scattered porosity, clustered porosity, linear porosity, and piping porosity, also called wormholes or non-standard term chicken tracks. So what's uniform scattered porosity? Uniformly scattered porosity is porosity that is roughly the same size and shape, and it's scattered throughout the entire weld. So you'll probably see this anytime that you attempt to do some gas metal arc welding and you forget to turn the gas on. Or if you're running flux core arc welding and you don't have an adequate arc length or contact tip to work distance. So a lot of times I'll see this, if the contact tip to work distance is too small, you're going to get uniformly scattered porosity because you're kind of burying that wire in there. You need to give that arc a little bit, or you need to give that wire a little bit more time to preheat before it enters that weld puddle so that it can do its job. So if you don't have an appropriate contact tip to work distance, or what they call an electrode stick out, you're probably going to end up with some uniformly scattered porosity. And the funny thing is as you're welding, everything looks all fine and dandy, and you're going through the joint and everything, and you get done with it, you lift up your hood, you go to clean everything off, and there's just porosity everywhere. So to eliminate that, keep your electrode stick out where it needs to be, and then make sure you've got good gas shielding. The next one up is clustered porosity, and that is a local grouping of pores that result from improperly starting or stopping the weld. So that's going to be either at the beginning or at the very end in the crater. So one thing you can do to fix this is, try not to speed up too quick. Strike your arc, let it burn in for a second, and then start moving through the puddle, and then make sure that you fill in your crater completely once you get to the termination of the weld. Also, you want to make sure that you don't have any cross breezes or anything going, that's going to blow your shielding gas out of the way. That's pretty much what's going to, cause clustered porosity. Again, arc length is probably going to be another culprit in this matter. If we pull back from the electrode, or if we pull back from the welding pool too far with our electrode as we're coming to a termination point, instead of holding right there and kind of trying to fill in that entire cross section of the crater, you're probably going to end up with some clustered porosity there. And that's just like a localized group at the end of the weld. Next up is a linear porosity. Now, linear porosity may be aligned a weld interface, the root of a weld, or the boundary between the weld beads. It's usually just like a straight line of porosity throughout the whole piece. Next up is piping porosity. And piping porosity normally extends from the root of the weld toward the surface. These elongated gas pores are also called wormholes. They do not often extend to the surface, and the porosity cannot be visually detected. So usually I see this with like your flux core arc welding for self-shielded and gas shielded. And we typically don't see this until we cut it apart to do a destructive test. Although we can find that with radiographic and ultrasonic testing. But typically, in my experience, I see this a lot when I go to cut a test plate open. We'll see it on the inside. So some of the things you want to do to make sure that you're not getting porosity in your welds, maintain appropriate travel speed, watch your shielding gas flow, make sure you're using the correct shielding gas, make sure your shielding gas isn't contaminated, maintain the appropriate contact tip to work distance or electrode stick out because, that's going to play a big factor in there. And then just watch your starts and your termination, and then make sure your weld metal is clean. I mean, that's the biggest thing is make sure you have clean base metal before you strike an arc on it. Otherwise, you're going to start pulling in impurities into the weld, especially like we talked about hydrocarbons, any type of grease, oils, solvents, anything you use to maybe clean the material. Maybe that's also you cleaned off, what you're trying to get rid of, but now you have a residue on there, and you're going to pick up porosity by doing that. So you want to make sure we got clean, nice base metal, clean filler metals. Sometimes with our gloves, we can contaminate surfaces, especially if we're doing gas tungsten arc welding. If we have nasty gloves and now we're running filler metal, clean filler metal right through our dirty gloves, you can get porosity that way. So just make sure everything's like nice and clean. The next discontinuity I want to discuss is undercut. So what is undercut? Undercut is a groove or crater that occurs at the toes of the weld. And when this weld flaw occurs, the weld metal fails to fill in that groove area, resulting in a weak weld that is prone to cracking along the toes. So if you think about it, let's say I've got a 3/8 plate that I'm welding on, and I weld across that, and I have a 1/16 inch undercut throughout the entire piece. That's not good because essentially what I've done, I've taken that 3/8 plate and I've reduced it down in thickness to 5/16. Now I've got like this nice, clean 1/16, depth of cut all throughout my material. So I've effectively reduced the thickness of my base metal, which is not good. So that's where your cracking is going to cause problems because it's going to rip right there at the undercut line. So that's why undercut is bad. So how do we cause undercut? Typically, the undercut's caused by improper travel angle. So case in point, let's go ahead and take a fillet weld for an example. Put the fillet weld in a horizontal position, okay? Because we only have to deal with a vertical plate and a horizontal plate at that point. Now, if I have my let's say we're using shielded metal arc welding. If I point my electrode too far at the horizontal piece, the flat piece that's on the material, I'm more than likely going to develop some undercut along the vertical plate, at the top toe of that vertical plate. Likewise, if I favor more of that vertical plate, I'm probably going to get some undercut on the bottom toe of the horizontal plate. So improper travel angle is a big cause of undercut. In addition to that, excessive arc length. If you think about it, what happens when we increase our arc length? If we're using shielded metal arc welding, we're going to increase voltage. Once we increase voltage, we drop our amperage. So now I have a much wider puddle. I don't have as much weld metal depositing into that puddle, and I'm most likely going to get undercut on both sides or, both toes of that weld. Another thing that's going to cause undercut is excessive travel speed. So if I'm going too fast, and this is, the problem that I see the most, especially with people just getting into welding, is they want to rush it. They want to strike that arc and they want to get going. They want to move really quick. Now, the problem with that is we have to give time to our filler metal to do its job. So that what that arc is actually doing, it's essentially cutting a trough into our base metal, melting our filler metal and base metal. It's mixing and then solidifying. So we have to give it time to do its job. If we rush that process, we're going to be left with undercut throughout the piece. We have to give that base, or we have to give the weld time enough to fill in all the little areas that we're trying to weld. So excessive travel speed is going to cause undercut. In addition to that, excessive travel speed is going to cause like a high ropey bead profile, which we don't want that either. We want a nice smooth flat weld regardless of position with even fusion into the base metal at the toes of the weld. Next up is incomplete fusion, which is often kind of misnomered as incomplete penetration. These are two separate discontinuities. So incomplete fusion is a planar weld discontinuity in which fusion does not occur between the weld metal and the base metal or between adjoining weld beads. So incomplete fusion is going to happen. I mean, we're not really going to be able to see this unless we're doing destructive testing or we're cutting something apart or we're using RT or UT on these different weld inspections. But essentially, anytime I've ever seen it, cut a fillet weld apart and you can see where that weld did not adequately penetrate into the joint. Or likewise, if I'm doing like a groove weld, I cut it apart and I can kind of see where that weld metal didn't really tie in to the bevel face. So some of the stuff that causes that is our amperage is too low. So if we're using shielded metal arc welding or gas tungsten arc welding, it's very simple. We can just reach over and we can adjust our amperage, turn that up a little bit. If we're using flux core or gas metal arc welding, that's very simple to fix too. We're just going to reach over and turn up our wire feed speed. That's going to give us some more amperage. I talked about this, and I believe it was Just the Tip Tuesday, episode number 1, the biggest myth in gas metal arc welding. So go check that out if you're not too familiar with how all that works, but your wire feed speed is going to increase your amperage. Likewise, a travel speed that is too fast is going to cause incomplete fusion, because once again, we didn't give our electrode time enough to do its job, where it has to melt the base metal, melt the filler metal. Those have to combine, and then it has to solidify. We have to give things time to do their job. And if we're traveling too fast, it's not going to work. It's just like Chef Boyardee, right? Good food takes time. Same thing with a weld. Good welds take time. So we have to maintain a good travel speed. That's why travel speed is going to be an essential variable with our welding procedure specs. We can't travel too fast or too slow, because both of those changes, or an increase or decrease in speed, is going to result in different welding discontinuities. We want to try to avoid those. Incomplete fusion can also be caused by a travel speed that's too slow, because now we're putting too much filler metal into that material, and it's not allowing it to melt into the base metal properly. So travel speed too fast, travel speed too slow, these can both lead to incomplete fusion. Now, on the same side of that coin almost is incomplete joint penetration. We typically see incomplete joint penetration on open root welds, or sometimes welds with backing, where it occurs when the filler metal fails to penetrate and fuse with the area of the weld joint. So if we cut apart a groove weld, whether it's open root or with backing, you're going to be able to see, that lack of penetration in there. The weld metal didn't quite reach the back side of that plate, which anytime we're doing open root welding, that's our goal. We want to try to weld the back side of that, or the inside of the pipe, from the outside. And what's going to cause incomplete joint penetration? Once again, our amperage is too low, so we have to turn up our heat a little bit, or the travel speed is too fast, because anytime we increase our travel speed, now we're messing around with our heat input. We want to get good heat input into the material, and if I'm traveling too fast, that's not going to happen. Another thing that can cause it is a travel speed that's too slow. So if I'm traveling too slow on this piece, my weld metal or my puddle is getting too big and it's not reaching the back side of that material. I'm putting too much weld metal in there and it's kind of getting stuck. So think of a funnel that's getting clogged. I'm not quite reaching the back side of that material. And improper joint penetration. So if we don't take time and we don't open up that root wide enough, I'm not going to be able to punch into the back. If I put too much of a bevel face on an open root weld, I'm not going to be able to punch through that and reach the back side. So we can always make adjustments. We can turn amperage up a little bit higher, or we can adjust our travel speed for that. So anytime we're welding, we always want to set ourselves up for success, and the best way to do that is to prep our joints properly. So make sure you have the correct bevel angle on there. Make sure you have the correct root face if you're doing open root. Make sure you have the appropriate gap set. And a lot of things you can adjust on the fly with technique. But you always want to set yourself up for success, and the best way to do that is to clean your material and set up the joint properly for the weld at hand. That's why we follow weld procedure specifications, because it's going to list things like, what your included angle is, what that root gap is going to be, what the bevel face is. So make sure you're following all this stuff as you go through. You don't want to just slam two pieces of material together and try and weld it out, because it's not going to work out really well for you, especially if you're kind of new to the welding process. All right, so up next is excessive reinforcement, and that is the excessive amount of groove weld which extends beyond the surface of the plate, caused by too slow of a travel speed. Well, typically caused by too slow of a travel speed. But anything, like I do a lot of work to D11, so anything greater than an 1/8 inch of weld reinforcement is considered excessive weld reinforcement, and we have to reject the plate at that point. Now, this can be the same thing for your root. I can't have any more than an 1/8 inch weld reinforcement on the back side of the plate or on the inside of the pipe, according to D11. I can't have any more than an 1/8 inch. Anything more than that, that's an automatic defect, and we want to try to avoid that. So just watch your travel speed as you're going through the material. One thing I recommend is getting either a VWAC gauge or a bridge cam gauge or weld reinforcement gauge as a welder, and making sure that you stay below that 1/8 level and staying above flush. So typically when I do a lot of my plates and stuff like that, I don't go to cap until I'm about a 1/16 below the plate, and then I'll go ahead and run the cap. That way I can maintain and make sure I stay under 1/8 of an inch. Now you're gonna have to check the code that you're working to, because some codes are different than others, and some are a little bit more stringent, some are a little bit more loose. So just make sure you're welding to the applicable code. Now next up is underfill, and underfill is probably one of my favorite discontinuities. And that's because they're very easy to fix. So underfill is a groove weld condition in which the weld face or root surface is below the adjacent surface of the base metal, caused by too fast of a travel speed. So the best thing about underfill is it's below the surface of the base metal, which is great, because now I can just add more weld metal, and then I can, just make sure I don't go above that 1/8 of an inch weld reinforcement, and I'm good. So underfill is great because it's a very easy discontinuity to fix. You don't need any special tools. Just got to throw some more weld metal on there. Next up is concave root surface, or suckback. Concave root surface is the configuration of a groove weld exhibiting underfill on the root surface. Whether this is on pipe or plate, we're trying to weld the backside of the plate or pipe from the front side. One thing that can cause this is a travel speed that's too fast. Once again, too fast of a travel speed is going to cause us a lot of problems. We got to give time, for these things to do their job. We got to give the time for the electrode to cut in and fill and melt and all that good stuff. So if we're going too fast, we can get sucked back. Another thing that's going to cause this is the root face is too small. So if I, put a 1/16 land on there instead of an 1/8 inch land, that could cause suck back. Also, if our arc length is too long, we can get sucked back in there. Another thing is if we put too small of a root pass in there, and then we go ahead and put a hot pass on top of that, what's heat do to metal? It moves it, and it's going to move it in the direction of the heat. So if I put like a flush root in there, and it looks all nice and clean, by the time I go to put my hot pass on there, it can, start pulling those pipes together, and it can pull that weld back into, the side that I'm welding on. So now I have, I've got underfill or suck back on the inside of my pipe or the back side of my plate, and you don't want that in there. That's the concave root surface. To avoid that, make sure you're watching your travel speed. Make sure, once again, you prep your joint properly and maintain a good tight arc length in that, and that should help alleviate that. All right, we're going to go ahead and take a quick commercial break. This segment of the Arc Junkies podcast is brought to you by Strong Hand Tools, makers of heavy-duty welding and fabrication tables, toggle clamps, and fabrication tools to help you increase speed and productivity in your shop. My favorite piece of equipment is the Rhino table. Now I can keep all my parts in place to improve accuracy and decrease heat distortion. And if you're a student and you want to register your school for a free gift pack of Strong Hand Tools, head on over to stronghandtool.com/arcjunkies and fill out the form. You're not going to be disappointed. Now let's get back into the show. The next welding discontinuity is called overlap. And overlap, we're not allowed to have any overlap according to D11. Now, overlap is the protrusion of weld metal beyond the weld or toe of the weld root. So I kind of explain this to people. It's like a beer belly, right? It's like that little, you got Dunlop on there, your belly Dunlopped over your belt. And what this is you traveled too slow with your weld metal. You created a lot of weld metal, and it's not properly fusing into the base metal, and it's creating like a little lip or a little belly at the toe of the weld. And any amount of overlap is an automatic defect. At that point, we're going to have to cut that weld back out and redo it. So what's going to happen is we're going to create almost like an acute angle between the overlap and the base metal. And on anything that's, holding up a lot of weight, or we have an excessive amount of vibration in there, or it's a cyclically loaded weld, that's going to start to propagate a crack underneath that overlap surface. So we want to try to avoid that. That's a sharp corner. We want nice, smooth transitions between the weld and the base metal anytime we can. So most of the time I see overlap, it's typically in a horizontal configuration, whether it's a horizontal fillet weld or a horizontal groove weld, where that weld's kind of like pouring over the edge because you're traveling too slow. So you want to make sure that you don't have any overlap whatsoever. If you're allowed to use a grinder and you have overlap, make sure you grind that down. You want a nice smooth transition between the toe of the weld and the base metal. You don't want to have that lump there. That's going to cause nothing but problems. All right, next up is an arc strike, which I'm all sure that, we're all familiar with arc strikes. And what that is a localized coalescence outside the weld zone. Arc strike is commonly used to describe a mark left on the material caused by misplaced arcs being started outside of the weld area. And the cause of this is very simple. It's carelessness, right? It was an accident. Things happen. So we want to be very careful. We're not allowed to have any arc strikes on the surface of our material. I know in D15, that's an automatic defect. We have to, we can't have any arc strikes on there. So we have to be very careful with that. So just make sure, when you put your electrode into your electrode holder, you strike an arc, be very careful, be very diligent of where you're striking your arc at. A lot of times, we'll just throw a rod in the stinger and we're moving around, whether it's a welding booth or out in the field or, wherever we're at, and we just bump the tip of the electrode across the material. Now we got an arc strike in there. Or the most common thing that I see all the time is as we're welding along, that rod gets stuck, and then we start wiggling that stinger back and forth, trying to break that arc. And as soon as it breaks, it kind of catches us off guard, and then we strike it right across the material. You don't want to have any arc strikes on your material. And the reason is because it creates little micro fissures. And in a cyclically loaded structure, if we have these little micro fissures in there, they can propagate through and they start forming crack formations. So we don't want to have any arc strikes on our material if we can avoid it. Sometimes we can fix this by grinding the surface back off. Sometimes, we're not allowed to use grinders. Arc strikes can cause a lot of problems. So, try to avoid arc strikes. Be very careful whenever you're loading a rod up into your stinger, and, just be very diligent about the type of work that you're doing. I typically use two hands when I'm striking the arc off, just so I can make sure I'm exactly where I want to be, and I get that electrode to strike off and fire exactly where I intend it to. So just be very careful and intentional, when you're striking your arc. Just pay attention. You can eliminate 90% of your arc strikes. And so if you do get your electrode stuck, the easiest way to fix that is just disconnect your stinger from your rod, let that rod cool down for a quick second, grab it at the base of the rod, and then wiggle it back and forth. You don't have any electrical current going through there. So once you break that electrode off, you're not going to cause any arc strikes anywhere. So just be careful. Best way to do that, just disconnect the stinger from the rod. So next up is slag inclusions. And slag inclusions are a discontinuity consisting of slag entrapped in the weld metal or the weld interface. The causes of this, inadequate inner pass cleaning. And I've heard time and time again out in the field, in the shop, all over social media, just turn it up 5 to 10 amps and you'll burn that stuff out. And it's simply not true. Take the time and clean the slag out of your material, because essentially what you're doing is you've got slag in there, you weld over top of it, now you've covered it up. You just can't see it. It doesn't mean that it went away. And if they do RT or X-ray on here, or they do a guided bend test, it's going to rear its ugly head and you're going to see it again. But the best thing to do is just make sure you clean all of the slag out. So anytime you're doing a slag inducing process like shielded metal arc welding or flux core or subarc or electroslag, pretty much anything that has flux as a product of the welding process, you're going to want to make sure that you clean in between passes. The best way that I've found to do this is get yourself like a decent set of dental picks from the auto parts store or off Amazon or wherever, but get a decent set of dental picks. You need like a straight one and then kind of like the L-shaped one or 90-degree shaped dental pick. What that's going to allow you to do is dig in between your weld or at the toes of the weld or anywhere where you have slag sticking that isn't coming out by a chip and hammer. Another thing you can do is you can use a wire wheel. These work very good. I've seen people use parts of hacksaw blades or saw blades. I mean, they work really well. If you got like a sawzall blade, you can get in there and kind of clean the corners of the weld out. Make sure you get all the slag out of there. Another area that people really don't look at is at the starts and stops where they're welding, especially if you're doing multi-pass welds and you have run-on and run-off tabs. They'll clean all the slag out of the middle, but they leave the stuff on the ends. And I tell people all the time, it's kind of like walking home from work and you cut across the front yard instead of going through the sidewalk and you step in dog crap and you walk in the house. You're pulling that stuff in there with you. So if you have a run-on tab or run-off tabs or wherever you're starting and terminating your welds, make sure that you clean the slag from those areas, because your weld pool can in fact pull that stuff in with it. And now you have it in your welding zone. And like I said, once you start cutting this stuff apart or doing different non-destructive testing, it's going to rear its ugly head and you're going to see it again. So don't rely on turning it up 10 amps and burning it out, because like I said, you're just covering it up. So try to avoid that. So next up is weld metal cracking, and we have to avoid weld metal cracking at all costs because I don't know any code book where cracks are acceptable. If I can see a crack, it's automatically fail. We have to cut that weld out and do that again. Weld metal cracking can usually be reduced by using low hydrogen electrodes. So what happens is we trap hydrogen inside of our weld metal, and that hydrogen, it wants to do its damnedest to get out of there. And so it's going to start propagating to the surface, and it's going to cause a weld crack. So there's actually a really cool video on YouTube called Hydrogen Diffusion Demonstration. Check it out. It's an amazing video, and it shows you exactly why we want to use low hydrogen electrodes whenever we can to reduce hydrogen under bead cracking or weld cracks. Another thing that can cause weld cracking is, like if we're working with aluminum and we don't fill in the entire cross section, we can get cold cracking or short cracking in that application. So we want to make sure that we eliminate cracks at all costs. Cracks are bad. We do not want them in our welding area. And then sometimes, depending on the grade of the metal or, the type of the metal, so like your cast irons, your P91 pipes, anything that's like extremely hard, you have to be careful with cracking because if we don't follow proper preheat, interpass temperatures, and post heats, we can also get weld cracking in there as well. So some of this stuff, you can't even inspect it for 24 hours after the final weld is made. Like you can't do anything. You got to make that weld. You got to sit back. You got to give it 24 hours before the inspector can come in and check it because that's when the cracks are typically going to occur. So you want to make sure that you don't have any cracks in your weld whatsoever because they're not acceptable by, like I said, by any code or standard I've ever seen. Next up, I want to change gears a little bit and talk about NDE or non-destructive examination. And that is the act of determining the suitability of a material or a component for its intended purpose using techniques not affecting serviceability. So non-destructive examination, we're not going to tear this thing apart. We're not going to cut it apart. We're not going to bend it. We're not going to do any of that stuff. These are all non-destructive. So that means that this weld's probably going to be put in service. So this is when you're welding up a component or you're welding up a building and the CWI rolls up on site and he starts performing some different testing techniques to check the soundness of your weld and make sure that it passes and it meets the intended standards or codes. Some examples of NDT or non-destructive examination are visual testing, also referred to as VT, magnetic particle, referred to as MT, dye penetrant testing is referred to as PT, radiographic testing or X-ray is referred to as RT, and ultrasonic testing, which we call that UT. So first up is visual testing. That's probably that's my favorite form of testing, and it's the oldest method available for testing welds. Welds are inspected visually using the aid of specific measuring tools to determine acceptance according to visual weld acceptance criteria. And as I said before, every code, every standard, they're going to have different acceptance criteria for the different types of welds that you're going to make. So depending on what code you're welding to, as a welder, you should be familiar with the visual acceptance criteria that you're being held to. You can actually pick up some of these tools right there on Amazon. You can swing into your local weld supply store. A lot of times they got them hanging on the shelf. But some of the tools that I typically use to do all my visual testing are obviously a fillet weld gauge. There's something called a VWAC gauge, which stands for Visual Weld Acceptance Criteria Gauge. These are great for checking undercut, checking porosity holes, checking underfill. I use something called a weld reinforcement gauge, so I can check the overall weld height, whether it's on the surface or inside the root. You can also use something called a high-low gauge. A lot of people that do pipe or, certain plates, checking misalignment, making sure everything's fit up properly. You can use a high-low gauge for that because some of the inspection starts before the welding even begins. One of my favorite tools is called a bridge cam gauge because I can check the bevel of the plate. I can check the weld sizes on that. I can check excessive reinforcement. I can check undercut. So it's kind of like, 3 or 4 gauges all in one. I love that tool. That's my go-to. That's the one I keep in my pocket. Anytime I'm doing weld inspections at the school or, out in town, if I'm doing any sort of weld inspections, I always have my bridge cam gauge on me. I highly recommend picking one of those up because, like I said, you can instead of buying 4 or 5 different tools, you buy that one for, I think they're like $70. Get you a gal. Gals are good ones, but it replaces a lot of the tools. So you don't have a whole crap load of stuff you're toting around with you. It's pocket size. You can drop it in your pocket. You don't even know it's there, but when you need it, bam, you got it. So like I said, get a bridge cam gauge. It's probably one of the best tools that are out there for visual inspection. That's just my opinion. Most of the stuff that I deal with anyway. Next up is mag particle testing. Now, this is the process for detecting surface and slight subsurface discontinuities in ferromagnetic materials such as iron, nickel, cobalt, and some other types of alloys. The process puts a magnetic field into the part. Now, if you've never seen mag particle testing, like do a Google search or check it out on YouTube. This stuff's actually pretty cool. They put a magnetic dust all over the weld surface of the material, and then they put this magnetic yoke over top of it between the weld. And as they're checking it, they're turning this magnet off and on, and they're blowing that magnetic dust across the surface. And what that does, if there's a surface discontinuity, that magnetic dust binds itself into like a crack or a pore or something that you really can't see with your eye, and it just kind of brings your attention to it. And at that point, now we can use some of our visual testing tools to measure the length of that discontinuity and find out if it's an actual discontinuity or a defect. So pretty cool stuff. Next up is dye penetrant testing, also known as PT. This stuff is really cool. The first time I ever seen this product, we were actually welding on armor plate in the Marine Corps, and just going through training and stuff, how to use different inspection techniques and how to repair cracks. But this stuff is really awesome. It's 3 different cans. They're spray cans. You get a cleaner. So once the weld has been made and it's cooled down back to room temperature, you're going to spray a cleaner on there just to get rid of anything that's on that surface. You're going to wipe it down, and then you're going to spray something on there called a penetrant, and you're going to let that soak for a certain amount of time, and then you're going to wipe that surface clean once again with the cleaner. Don't spray the cleaner directly onto the weld. You're going to apply that to a rag and then just wipe in one direction across the surface. And then after that sets for a minute, you're going to spray something on there called a developer, and it's got like a dwell time on there. And what this stuff is, it uses capillary action, and it pulls and penetrates into the surface of the weld. So if you have any discontinuities, this penetrant is going to get inside of it, and then when you spray that developer on there, boom, it's going to light up, like really bright red. You're going to be able to see this stuff for freaking miles. But now, once again, we can use our inspection tools and start measuring it. This stuff's really good for detecting cracks in the surfaces, especially if you can't see it with your naked eye. One thing I like to do when I teach using dye penetrant techniques and stuff like that with the students is, and especially if you're a welding instructor, you got to try this. Whether it's a fillet weld or a groove weld, get you some like number 10 ground wire, copper ground wire. Cut you off like a little inch or 2 piece. Make sure it's nice and flat. Drop it right there in the fillet weld or the groove weld. Weld right over top of it with either 70S6 MIG wire or 7018 stick wire, and just weld it up all the way to the surface. Now, the cool thing is 9 times out of 10, you're not going to be able to see the crack that it produces with the naked eye. So you can pass it around to the students and say, hey, is this acceptable? Would this weld pass? And they look at it and are like, oh yeah, everything looks good, because you really can't see the crack. And then you grab the dye penetrant testing solutions, you go through that whole process, and then boom, you see this big crack in there that you really couldn't see with the naked eye. So it's really cool stuff. You got to try it out. That's something that Bob Moffett taught me. For a long time, I was trying to figure out, how do I simulate a crack so I can show that this product actually works? And Bob, he told me, oh yeah, just throw a piece of copper in there. And the best thing I found to use is like number 10 grounding wire. So give that a shot. Next up is radiographic testing, also called RT, and this is X-ray, very similar to going to the hospital and getting checked for a broken bone or something. This method of testing makes use of X-rays produced by an X-ray tube or gamma rays produced by a radioactive isotope. It's the basic principle of radiographic inspection of welds, and it's the same for medical radiography. So like I said, whether you're going to get your bones checked out or whether you got to get your weld checked out, it's pretty much the same thing. And they can do this stuff in an X-ray box at a testing facility, but there's also trucks and there's mobile equipment where these guys can come out to the site, right there on the job site, and they can check the pipe or, whatever you're welding on, they can check that and get X-ray film and show exactly, what type of discontinuity you have and where it's at. The problem with this stuff is you really can't check the depth, but you can see where the discontinuity actually is, and then you'll be able to cut that out and then make that repair. Next type of process for testing is called UT, or ultrasonic testing. And this method of testing makes use of mechanical vibrations similar to sound waves, but of a higher frequency. And a beam of ultrasonic energy is directed into the object that needs to be tested. So in this case, it's going to be right there into our weld. This beam travels through the object with insignificant loss, except where there's an interruption and reflected by a discontinuity. So once again, they're going to be able to tell you exactly where that discontinuity is by using ultrasonic testing, sending these little sound waves in. It's going to bounce off. It's going to come back. They're going to get a reading, and it should relatively be the same reading throughout the piece unless there's a discontinuity in there, at which point, they're going to tape it off. They're going to mark it off, and they're going to say, hey, you've got, some sort of a problem here. Go ahead, cut that open. Let's check it out, and then we'll go ahead and make a repair. Okay, the last method of testing is probably my favorite, and that is destructive testing, because this is the stuff that I like to really nerd out on. And we use destructive testing for a lot of things. Most of the time, if we have to qualify a procedure or qualify a process or certify a welder, qualify a welder, whatever the case may be, what we're going to have to do is we're going to have to tear the weld sample apart. So this is obviously something we're not going to put in service. This is a weld we're going to make intentionally to cut up and destroy and test how well this stuff is going to perform given the requirements. So we can develop a procedure to, for specific filler metal to base metal conditions, different temperatures, different welding processes on different material thicknesses. It's really cool stuff. So if we're going to develop a procedure, we're going to weld up a larger piece of material. Typically when we do weld performance qualifications or certifications, it's usually a 6-inch coupon. Well, with a procedure qualification, it's going to be much larger, usually for groove welds like 24 inches. And that's because we have to pull tensile pull specimens out of there. We have to do guided bend tests. We have to do Sharpie V-notch tests, if it requires that. So it really depends. But we're going to use this stuff. We're going to completely destroy it once it's over. And then for welder performance qualification, we're gonna break those as well. So that's either going to be root and face bends or a fillet weld break test. It's a really cool process. There's a lot of great videos on YouTube on how to do some of this stuff. But ideally what you're going to do is you're going to take the weld sample. The first thing we're going to do is we're going to perform a visual test on there, because if it doesn't meet the visual acceptance criteria, it's not going to go to the next stage in the process. So typically if we're qualifying a procedure, we're going to do a visual inspection on there. Then we're probably going to do a RT inspection on there. And then we're going to send it in, and they're going to water jet all these different samples out of there. We're going to machine them down. We're going to take the backing strip off, and we're either going to do tensile pulls, Sharpie V-notch, or guided bend test. So it's a really cool process. Like I said, probably one of my favorite, because you can get instant feedback and instant data. So like the other day I did some fillet weld break tests for a company, and it was really cool, to kind of navigate into a different code book I'm not familiar with operating in. But once you understand how to read one code book, you pretty much understand how to read all of them. You just have to look at the different requirements. But it's really cool because, you get instant feedback of the weld. Is this a sound weld? I don't know. Let's break it open and find out. So for a fillet weld break test, we can check and see if we got good root penetration. We can do macro etches on there, to see if we punched into the root. If we're doing weld qualifications or some weld procedures, we can actually cut the groove weld apart, and then we can look at it and make sure we're getting adequate penetration in there. Take the backing strip off, grind the root face down, prep it, for a guided bend test, and then bend it. And this is where I typically see your slag inclusions come back up, that you said we were going to weld over top of, and, we'll just burn it out with 5 to 10 amps more. I see lack of fusion in there, lack of penetration. This is where all this stuff comes to fruition. So just because the weld passes visual doesn't mean it's still a good weld. So we have to go to the next step and do either destructive testing or like some of the other testing methods we talked about, whether it's RT or UT. We're going to have to go through all these different test procedures depending on, what's the purpose of this weld? Is it for qualification for a person, or is it for certification for an individual, or are we qualifying a procedure? So it really depends on what we're doing. But I think guided bend tests and destructive testing, they're a lot of fun. Well, that pretty much covers weld quality as it relates to weld discontinuities, weld defects, and weld testing. I hope you all enjoyed the episode and learned something new that's going to help you along on your welding journey. Remember, all discontinuities are not defects, but all defects are weld discontinuities. That was my biggest takeaway when I took the CWI exam was preparing to become a CWI, especially coming from the background as a welder. Because I always thought, and I was always under the impression that I couldn't have any discontinuities whatsoever in my welds. But as I learned going through the different seminars and classes, reading the code books, and now teaching the material, there's allowable limits for discontinuities before we can reject it for a defect. So remember, some codes are more strict than others, so just make sure you understand what's applicable in one code may not be applicable in another. So, just kind of keep that in mind. And then as a welder, whether you're welding to structural requirements or you're doing API or ASME, each different code is going to have a different standard. You know, the Canadian Welding Bureau, they have different standards than we do. Although we have a lot of similarities, there's also a lot of differences. So just make sure you're familiar with the code that you're working out of as a welder. Before we get out of here, I just want to ask you all, if you have been finding value in the content of the ARC Junkies podcast, please feel free to leave a review on your favorite downloader app. Share the show with anyone you know that has a thirst for welding knowledge. You can subscribe to the show on arcjunkies.com so you never miss an episode. I have new stuff coming out all the time. Got regular Monday shows, Tuesday shows, Weld Wednesdays with AWS, and then every once in a while I got bonus shows coming out. So if you don't want to miss anything, make sure to go over to arcjunkies.com and you can sign up so you can get a notification every time I drop a new episode. Don't forget to check out Just the Tip Tuesday. I got another episode coming out for you tomorrow. We got Weld Wednesdays with AWS, the first Wednesday of every month, right here on the ARC Junkies podcast. I appreciate each and every one of you. Stay safe out there, and until next time, make every weld better than your last.